Okay, so here we are. 2.2a is an alpha in college algebra, and we're going to be looking at fitting lines to data points, modeling linear functions. And as I'm talking, I'm trying to get a graph on here so that we can have one to look at, since most of this section is just going to be on graphing. So first of all, we're going to look at exact and approximate linear models. And one of the things that's really important is to know that if you have a linear model, a graph of a linear function, such as in the form of y equals mx plus b, it's going to be a straight line, and the slope is going to be consistent throughout the entire graph. You just need 2 points, you draw your straight line, and you've got your graph. Okay, so example number 1 talks about what is called a discrete function, and that is when we have a finite number of inputs. So for this particular example, we have at year 21, we have a retirement payment of $40,950. So let me get a picture of that on here for you. Okay, so with that picture, notice we're taking the table 2.3 at the top of the page, and we're making a graph which is at the bottom of the page. So when we are with this university 21 years, we get a retirement of around just under 41,000. 22 years, we're there around 43-ish thousand. 23 years, we're up here. Notice our years again are along the x-axis, and that's going to be pretty consistent. And we graph these, and when I say a discrete function, that means that we're not talking about points between here. We're talking about individual points, that there are a finite number of points here, that a certain year you make a certain amount of money. But what we're going to do then is we're going to draw a line to connect all those dots, and that gives us an equation. Y equals our slope times x. And there is no y-intercept here, because notice the graph stops at y equals 0. Okay, you're not going to lose money. You're not going to be in the negative area here as far as dollars are concerned, so we stop there. All right, and we go all the way up to, well, where the graph stops at age, or 25 years with the university. So that gives us that, just a line segment there, and that's discrete. Okay, a continuous function is one that can be drawn over its domain. Domain is this way. So it can be drawn starting here all the way up to here to where you stop without lifting your pencil off the paper. Okay, that makes it continuous. This one's discrete because we put a dot, lift our pencil, dot, lift our pencil. So each one of these we're lifting our pencil to do. When we draw this line, it's continuous, and we do not lift our pencil from the paper. So that's just kind of a real easy way to say that. So if we know that our line is a straight line, and it's not an estimate of a straight line, then it is an exact linear model, or a linear graph of what we've got. Now, when we get to example 2, we're looking at the population of females under 18, and we're going to get an estimated linear model here. So let me get a picture of that on here for you. So again, we're dealing with years and then population. So the graph down here at the bottom did the same thing we've done in the past. We put our years down here, okay, and we put number up here. Okay, so this is the number of years after 2000, because if you look at the instructions here, it says draw a scatter plot of the data with the x value of each point representing the number of years after 2000. So, 2020 is the earliest one, so that's 20 years after 2000. So that is going to be where we start here. Our x number is at 20, and at 20 we are at 37.2. Okay, 37.2. When we are at 25, which is here, we are at 38.2. So notice we're putting our dots on here. Again, a discrete function. And notice that our dots are not giving us a real straight line. In fact, as we bring this closer, you can see that that's not giving us an exact straight line. So what we have to do is we have to do what is called a best fit line, which means we are going to try to draw a line. See if I can make this work here. We are going to try to get a line that kind of fits this the best. Okay, it's called a best fit line, and we try to get these lines in here as close to all the points as we can. Okay, so because of, well, let's see, maybe we should move that hair up a little bit like that. Okay, so after we draw that best fit line, they're asking us for C in example 2 to find a line through two of the data points that is a good visual fit for the points and use the 2 points to write the equation of a line. Alright, so they picked for their example, and we'll just pick the same ones for ours. So for their example, they used this point right here and this point right here. Okay, and it doesn't matter which ones you pick. You could have picked this one or this one. You know, it doesn't matter. As long as you have 2 points, then you are able to write the equation of this line, which is what they want you to do. So this is point 25, 38.2 from the information they gave you, and this is point 60, and it's 43.6, again from the table that they gave you on page 107. So given that bit of information, we are able to write the slope, which is going to be the difference in the y's, over the difference in the x's, giving us a slope similar to, put a little squiggly thing up there, means it's going to be close to, it's just an estimate, it's not exactly equal, of 0.154. Okay, so that is the slope. Alright, so what we're going to do is we're going to use the y minus y1 equals slope x minus x1 formula here, and let's go to black. So we have y minus, and it doesn't matter if you pick this point or this point. The book picked that one, so we will do that one. So they're going to take the difference in the y's equals 0.154, which is your slope, times x minus 60. So there's your equation. All we have to do is simplify it now. We're going to add this to both sides. And that's going to be 34.36 because we're going to distribute 0.154 times negative 60, add 43.6, and that's going to give us that. So this here is the equation of this best fit line. Okay, so that gives us an idea of what that line is. Alright, so let's continue on to fitting lines to data points and linear regression. And we will do that on the next video.